Hi folks, this is a follow-on from my last video where I featured Mike, a retired F-16 pilot, and he was contemplating some of the anomalies that he now realizes when he thinks back to his pilot days with the radar systems, and in particular how they would work on a globe. So I want to follow on from that video and just expand on it a bit more. Now this isn't anything to do with over the horizon radar. Nothing that I'm going to be talking about is blocked by any curvature. This is all line of sight stuff, even on a globe. But the elevations that the aircraft are flying at is intriguing, and how the radar systems actually determine what elevation that these aircraft are flying at. So first of all, I'm just going to let this guy from a radar integration systems design company. I just want to let him talk about the basics of radar first, so we get a bit of a grounding on how exactly it works.
Hello, this is Roger Hosking, and today we're going to present a radar tutorial which gives some of the basics of how radars work. What is radar? Radar is an acronym for radio detection and ranging. As you may know, electromagnetic waves reflect off objects like light rays reflect off a reflective surface. Radars send out pulse signal and look for a reflected return signal pulse. And you probably also know that radar signals, because they're electromagnetic signals, travel at the speed of light, or 300 kilometers per second. The time it takes for a reflected signal to return back to the antenna is twice the distance divided by the speed of light. But useful radars also need to detect the target location, not just the distance. And advanced radars can detect multiple targets, the speed, the heading, the size, as well as the identity of the target craft and perhaps even the country it's from. The next radar we'll look at is called monopulse radar. It locates a target with a single radar pulse, and it uses a multi-element receive antenna. 3 signals are delivered from the antenna down to the radar processing system. The first is the sigma, or sum signal, that is the summation of all of the 4 different patches. The second is the delta A, which is the delta azimuth, which subtracts A1 minus A2 in signal. And the delta E is the delta elevation, which is E1 minus E2. Those 3 signals go down to a signal processing engine that calculates the phase shift between the main sigma or sum signal and the delta A signal. That allows you to determine a very accurate azimuth angle of the target. And the phase shift between the sum and the delta E signal determines a very accurate elevation angle.
Okay, I'm going to try and draw what's going on here in AutoCAD with these antennas. So we've got a jet aircraft here. We've got the antenna represented by this white line here in the nose. E1 and E2 are the 2 elevation receivers, and the white line coming out here represents the center line of the antenna, and that is perpendicular to the antenna itself. So that's the reference point for the antenna. It knows exactly where 90 degrees is. So the purple lines represent the beam, and they obviously diverge as they get towards the target. So if we zoom right out now, I've drawn another aircraft at 40 miles away. Zoom right out. Obviously the beam continues to get larger, but at 40 miles we've got a target just here. Now obviously the target is above the center line of the beam angle. So the purple lines represent the pulses hitting this target, and it hits just here, and a return pulse is generated, and this returns in this direction, represented by these lines here, and these lines are 90 degrees to the return pulse. So if we zoom out, we can see that the return pulse looks parallel to the center line, but the further we get out, you can see it's getting closer and closer. And if we go back to the antenna, we've got these return yellow pulses here, which are 90 degrees to the center line of the line to the target. And when they get to the antenna, you see the yellow line here, it's obviously going to hit E1 before this same pulse hits E2 here because it's closer to it. Now the distance, the physical distance between E1 and E2 is known. So using simple trigonometry, you can determine the angle of elevation to the target. Now you'll note that this has to be incredibly precise. You can see how we're talking nanoseconds here. It's going to hit, this one's going to hit there nanoseconds before this one. Okay, so a slight inaccuracy in the angles here, and it's not going to work. It's going to give errors. Here I've taken a snapshot of some of the different angles in which a pilot can set his antenna in order to scan a particular section of the sky. These are typical upper and lower elevation limits based on a maximum range of 40 nautical miles. These limits are displayed here. Let's say the jet is flying at 10,000 feet and the pilot tilts the antenna to achieve this position. The upper portion continues to grow with increased range, but the bottom remains at the altitude of the aircraft, i.e. 10,000 feet. In this situation, the radar will not detect anything below 10,000 feet. So up to now, everything's been intuitive, logical. You can see how it works. The radar is essentially an angle measuring device, much like a sextant, except it measures angles to physical objects rather than the luminaries, and it can also measure azimuth as well as elevation. But essentially it's just a tool to measure angles. Now let's start to introduce globe geometry into the mix, and things start getting real crazy to the point where I'm not even sure what it is they're claiming that happens. Probably you'll be as confused as I am by the end of this. So there are two main problems as I see it. One is the drop due to curvature, and the other is the ever-changing atmospheric conditions in the region between the antenna and the target. Okay, let's deal with the drop due to Earth curvature first. So I've got an example here. The blue is the Earth curvature drawn to exact scale, 3,959 miles. If I zoom in to here, we've got one aircraft. He's going to be doing the detecting. So his antenna is sending out a signal represented by the purple line. And he's at 10,000 feet. So his signal, the bottom of his signal, is also at 10,000 feet. Okay, we've got another aircraft here, also at 10,000 feet, just here. So obviously the bottom limit of the radar here is above this aircraft. So theoretically it shouldn't detect it. The only way that the other aircraft would be able to detect this one would be if he was to lower his antenna beam by 1 bar. So let's do that. The aircraft here is now within the beam signal, so theoretically would be detected. However, he is 1.82 miles lower than the 10,000 feet mark displayed on the radar screen within this aircraft. So some sort of exponential function would need to be included within the calculation at the radar processing stage for this to be able to be calculated and for the correct elevation to be shown on the radar screen for the pilot. I would suggest that something like the 8 inches per mile squared or something similar should be input into the processing system for it to be calculated. All that goes out the window, however, when you do an image search for super refracting duct. This is what comes up. What they appear to be saying is that the signals are bent all the time, and the degree in which they're bent are divided into 3 classifications: super refraction, standard refraction, and subrefraction. But essentially all of them are bending the radar signals. So super refraction is used to explain why some objects that are beyond the curvature and should not normally be seen are seen by the radar. Now, superrefraction follows the curvature of the Earth. So signals will be sent over the curvature of the Earth, and if you look at this one here, you'll see that it creates what they call a duct. This one's a superrefracting duct, and the signal is trapped within this superrefracting duct, and that's how it can get around the curvature of the Earth and see things that would normally be blocked. Okay, normal refraction, so in normal conditions, the signal's being bent up, okay, away. Anything higher than superrefraction is normal, I guess, but the point is it's being bent up, away from the Earth, and then superrefraction is obviously even further. Okay, so let's focus on this image produced by the US Navy. Let's say that this is an aircraft flying at 10,000 feet, and anything along this dotted line here is also at 10,000 feet. Which one of these conditions is more in line with this? I would suggest it's superrefraction. And I would also suggest that superrefraction must be occurring 100% of the time for a radar to function correctly. But that isn't correct, because, as referenced here, the presence of surface ducts and elevated ducts, especially over land, are extremely difficult to predict and may persist for very short periods of time. The atmospheric conditions favourable to duct formation are difficult to predict using conventional weather forecasting techniques. So there you have it. Superrefracting ducts, or superrefraction, is only invoked to explain why some objects are able to be detected beyond the horizon and are not a normal occurrence. So let's say it's a normal day, no superrefraction going on, no superrefracting ducts, no line of sight issues, there's nothing being blocked by any curvature. We've got a target here that's 10,000 feet in altitude, and using the example from earlier of 120 miles, so this distance is 120 miles, we had a 1.82 mile drop. Yes, that's miles. Nearly 2 miles of drop here, okay, to the target. So what they seem to be saying is that under normal conditions, the signal is being bent upwards. So we've already got a 1.82 mile problem here, but the signal is being bent up and away under normal conditions. What I'm saying is that only during superrefracting conditions can this target, or any target along this dotted line, be seen and an accurate elevation angle determined. But then again, even that's wrong. You can't actually get an accurate elevation if you've got bendy radar signals. And here's why. I've drawn an example using superrefraction. So the bottom of the radar signal now is following the curve of the Earth exactly, 10,000 feet. The top is also being curved, and then I've drawn a center line, which is the halfway point between those two lines, all going all the way back to the aircraft here. So again, I've placed another target aircraft here. So let's say that the beam, represented by the purple line here, reflects off the aircraft and sends out a return pulse, this yellow one. So at that particular point on this line, this pulse intersects this line, so it's perpendicular. But because this is a curved line, every single point along here is going to be a different angle until this angle now is different to what it was back at the target aircraft. And I'll show you an example of this because I've taken a screenshot. This screenshot is from the target aircraft end, and if I put it next to this one, you can see that the angle is different now. The implications being that when this pulse here hits the two receive antennas, this angle is going to be different to the angle in which it actually was reflected from the target aircraft. So it's absolutely no use whatsoever. The radar system could not possibly calculate what that angle was. But that's under super refracting conditions, and normally that doesn't occur. That's just odd occurrences when the weather permits. So normal conditions then, what I've done here is I've rotated everything up very slightly. So the bottom part here is no longer following the curvature of the Earth. It's up. Everything's gone up very slightly. Well, it doesn't really help matters in terms of detecting anything. You've still got the bent lines. The return pulses are still going to be at a different angle to what they were when they were reflected off the target aircraft. But you've also got the added problem now that because it's gone up, the aircraft here flying at 10,000 feet, which should be absolutely no problem to detect, it cannot be detected because the bottom part of the beam has been refracted upwards due to normal atmospheric conditions. Up to now, I've been humouring the notion of bendy radar signals. The truth is that once a pulse has left the antenna, it has no idea of the conditions out ahead of it. It doesn't know whether the atmosphere is refracting, super refracting, or subrefracting, and therefore any data fed back to the signal processing system is pretty meaningless. Okay, after saying all that, there is a way that all of these problems go away. The elevation angles work. We don't need to worry about refraction. We don't need to worry about targets being seen beyond the curvature. Everything works perfectly, and that is on a flat Earth. Now I know that will trigger some people, and if you are one of those people, I invite you to show me exactly how radar systems detect elevations of other aircraft on a globe using similar methodology to what I'm using here. If you haven't got AutoCAD, then you're welcome to come on a Skype call with me and you can run me through it. I can draw everything, and you can explain to me exactly how it works with these two elevation antennas and how they can measure angles from bendy signals. And I'd also like it backing up with citation as well, because this sort of thing must have been thought about, surely, if we do live on a globe. My email address is in the description below for anybody who thinks they might be able to explain this. Thanks for watching.